Okay, physics, let's do this. We got a new thing, right? It's, you can see, nope, this way. You can see that way. We talked the position time graph, we talked velocity time graph, how they're, linked, right? More than that, the math here is linked to the equations that you saw, and it's linked to acceleration too, right? We haven't touched acceleration in graphs. If we think and we look, and I'm gonna get a little fancy here. Found some new stuff that I can do. If I were to look, if I were to make a position time graph that looked different than the ones we've seen. So all the ones we've seen have been like, moving forward, moving backward, not moving, right? But it's usually not the case. Usually, our motion will look something like, let's see, let me think. I'll do this. I'll draw, and I won't start at the origin just so that you can see what's happening. Let's draw a position time graph that looks like this. And this is a lot of time. I'm not going to look at this much time. I'm not going to look at this much distance. I just got excited with that ruler thing. So here, let's look at this position time graph. Let's actually make it a position time graph, right? Okay. This is an object that is traveling. It's moving because its position is changing as time moves on. It's moving forwards because it's going, it's getting more positive. It's going up. It's getting positive on the y-axis, which just means it's going in the positive direction. So up, right, forwards. Let's call it forwards. But it's not moving the same pace the whole time, because if I were to draw out little time hash marks for the motion of the object, if you look at this first section compared to the second section, compared to the third, and so on and so on, we're covering more distance. Every time interval, every time piece here, we're covering more and more and more and more distance, which means that we're going faster and faster and faster and faster, and our word for that is acceleration. Like, that's a traditional acceleration, you're just getting faster. This is a very typical position time graph for what you might see. And a situation that might go with this might be something like a runner starting at the blocks, from rest, sprints forward. A runner starting at the blocks from rest sprints forward. Alright? And let's actually give these some values here. I'm going to say that this 12, 7. Alright, so let's take my ruler back. And I'm going to draw a dotted line here. Just to, let me, right, so just because I want to do a little math here. I want to do a little work here. Right. What's going on? Let's relax there, huh? Hey, there we go. Ooh, that one worked nicely. Look at that. I love it when a plan comes together. Little dashed line here. Okay. So, let's say that each of these just represents a 1, right, for ease. So this is 1, 2, 3, 4, 6, 7, 8. This is 9. 1, 2, 3, 4, 5, 6. Alright. So, what this says is that after 6 seconds, this runner, who started at 2 meters, has traveled up to 9. So they traveled a total of 7 meters. Right, so previously, if I asked you for the velocity of this object, for this runner, right? Velocity is distance divided by time. How much distance was covered? Well, 9. So 9 meters minus 2 meters over 6 seconds minus 0 seconds. Well, that's 7 meters over 6 seconds, and that's 7 over 6 meters per second, because I don't feel like dealing with the decimal place right now. Just not going to. I was hoping that my drawing would work, but it didn't. It is what it is. Okay, but is the runner traveling the same speed the whole time? No, they're not. They start out slower. Right, if you look at this, if I were to look at like the slope here, right, at this spot, if I just drew a straight line slope here, it's definitely not the same as it would be in the next spot. It's not the same as it would be over here, and so on, and so on. And so, right, yeah, I could keep doing this. Because the slope is constantly changing, the velocity that I just solved for this velocity is an average, right? I just took, how far did we go? How much time did it take us? That's an average of 7 meters, 7 over 6 meters per second. Right, early on, down here, we're probably not going that fast, and up here, it looks like we're going faster than that. So how do I figure out what the velocity would be at any given point? Alright, this, with a graph like this, when you have acceleration, I can no longer just use this equation for velocity. And it also actually isn't enough to only know that acceleration is velocity over time. I need to somehow combine, right? How do I combine these things? How do I find a way to merge them into a single equation that links, you know, velocity, acceleration, time, and distance? Right, and this is just my introduction to the next equation, which is going to be a big deal. No, it's not. I'm just gonna stick to the graphing first. I can work with just these two equations and do some graphs. This is going to be a hashtag soon. Soon we will learn how to do that. For now, what we're going to do is, how are we going to make a velocity time graph and acceleration time graph, right? So I'm going to focus on the shapes first. I'm not going to worry about the exact numbers yet. We'll get there eventually, and that will be when we do the math. But right now, let's focus on the graph and the shape. So, if I want to compare this, I'm going to make two, oh goodness, please stop. Actually, yeah, do that, because I want to make two of these graphs. I'm going to make velocity time and acceleration time. We'll make them both right down here. Let's do this. Let's do this. And then let's do this. And missing it. That'll do. And let's do this. Okay. So, what are you doing? There we go. Let's call this guy velocity in meters per second, and let's call this time in seconds. Let's call this acceleration in meters per second squared, time in seconds. Now we said that this kind of starts pretty low, and every second it seems to be getting just the tiniest bit faster. I'm going to extend this one a little bit, but this is kind of a representation of what's happening to velocity. Covering a little bit of distance, then a little more, then a little more, a little more, etc. So we're speeding up each time. Right, I could do a calculation at each point here and figure out how much we're increasing, kind of. But this is what's happening. The velocity is constantly increasing. Right, because the amount of distance is a little more for each period of time. The acceleration is how is velocity changing over time. Well, for each moment, velocity is changing the same amount. So every moment, every second, velocity is changing the same amount, which means we said the velocity was constantly changing. So the acceleration is going to be a constant. It's going to be a constant number. It's the same acceleration throughout. Our runner is accelerating at a constant pace. They're accelerating at a constant pace, which means their velocity is constantly increasing, which means the amount of distance that they cover is definitely increasing. It's constantly increasing. Alright? This is one of the connections. This is one version of a position time graph that shows acceleration. There are several more. We'll talk about those during class. We'll talk about how to match them to each other. That's what the quiz will be on your F day. Alright? Keep these examples in mind. And yeah, keep these examples in mind. If you have any questions, bring them for class. In the meantime, I will catch you later. Take care, kids.